fluid movement between LLM and code. Sorry. But yeah, I think you have read the title, and we can go on. So maybe I will ask the question, who is a programmer here? How many? Okay, great. So because it will be pretty technical presentation. So another question is, who has heard about recursive language models? Okay, great. So let's go. So the title is about moving logic between LLM and code. And it will be about my library that I am just writing now. I call it a hybrid virtual machine, or maybe recursive LLM harness. It's built on Pydantic AI. And yeah, and it is designed for this kind of movement of logic between LLM and code. Okay, so it starts with the simple observation that prompts are very much like code. So there are instructions that will give computers to do something. So with prompt you can do this, and with code you can do this as well. But there are differences. So there are differences, well, everyone understands what the differences are. The code is deterministic, fast, and cheap, and while prompts are more flexible, but also are much slower. So the ideal machine would be one that understands both. So a hybrid virtual machine. This is what I am aiming at with my library. Neither mode of execution dominates. You need both, and you need both in every corner, because computation is fractal. Computation is basically recursive. So why not domain-specific languages? So if you go with LangChain, they do those graphs of agents. They try to organize the agents in graphs, and when you start doing this, it seems like it will cover everything because, well, it's so general structured, but then you come and with each new case you add something to this, and eventually it's not anymore very specific language. You eventually get to a general purpose programming language with this. And why not start from a general purpose language at once, from the start? So I've started with Python. So why recursive? Because our thinking is recursive. When Turing was thinking about how people was trying to formalize how we do math and how we reason, then, well, this recursion was the most general way of doing this. And basically, what we see with the tool loop, it's just one level, and it's not enough for doing general thinking. And yeah, basically, here we have a concrete example of a thinking like trace, and some parts of the thinking is judgmental that could be done by an LLM, and some are mechanical that should be executed on code most efficiently. So what this shows is that we need this interleaving of mechanistic and neural computation. And one layer of LLM calls tools, even with a loop, would not be enough for this. For the full power, we need Fractal and we need recursion. So There was a paper last year. Well, actually, there were two papers. The last one was from October, I think, about recursive language models. They have formalized this. But actually, what I believe is that many people have been thinking about this earlier, but their system has a big advantages, which is that it's very simple. So it's very easy to run it on the test cases, and you can publish papers with this and show how efficient it is in comparison with other approaches. So they formalized this, and they had this idea to give the LLM REPL as a tool. And basically, that was the only tool that the LLM had. But it's very universal because it can execute any code. But this code is sandboxed, so it doesn't have any side effects. Everything is very functional, and there is no reentrant state. So that's what makes this approach very simple, because basically functional approaches are simpler to reason about and also to implement. Yeah, and also this code is ephemeral. So the LLM writes the code executes, and then it is discarded. It's not used anymore. But I was thinking more about evolutionary software. So I have arrived at this very similar architecture, but with different priority. They wanted to have something to show the power of the system, and I was more interested in the engineering approach, in the way how we program systems right now. And for me, there was this very important thing was to make the system evolvable, so that if the LLM if you have a code that executes, then we store it, and next time we have the same task, we reuse this code, because if it was working last time, then next time it will also work. So, and if LLM is to write the code again, then maybe it will write something wrong. So that was the thing that's actually it will be the next slide. But basically the idea was also about a system that is extended with natural language. So you tell the LLM, you have a computer system, you tell it what to do, and it interprets it. And next time and this interpretation is saved somehow. So basically it can be saved as a program or as a prompt. And over time, when you learn your tasks, or maybe the LLM understands what parts of this process are always the same, what parts can be converted into code. So these are the differences between my approach and the recursive LLM's approach. So in my case, the code is stored and evolved. They have this REPL idea, which is very, very good idea, for a system that doesn't do much like outside, that doesn't do any actions on the outside, so that it can be sandboxed in a place and just compute. But if your system does act on the outside world, then you want approvals and maybe you want stateful tools like database connection and stuff like this. Okay, so the LLM system is very elegant, but I think it's also very limited for practical application. So why not ephemeral code? So I already told about this. Basically, ephemeral code is very good for benchmarks because you run the benchmarks, you can show that it executes well, then you throw away the code. But the software that we use now, like I don't know, Word is for editing documents. Browser is for browsing the web. Each tool has a task, has a specific task. And this way, we can accumulate knowledge about this task, this particular task, like the writing a document, and we can improve the code with time. We can add features, and it accumulates our understanding of this task. But if we throw each time the code away, then there's no learning with this. Maybe at some point we will have those LLMs that understand everything, and you tell them, okay, now I want a browser, and it writes you the browser. You use the browser, and then you close it, and it goes away. But for me, it's like very crazy ideas, and still I don't think that it can be a general approach for system programming. So my idea is about something that grows, like so that's just an image of something that grows layer by layer, and that's the metaphor. So yeah, what were the core design choices in my system? So I also decided that unified calling convention will be very important, because when you have this software that evolves, then refactoring will be very important. And then when you refactor something, then maybe you will change from code to a prompt, or maybe from a prompt to code, and you don't want to change the call side, the program that uses this piece, this agent or maybe this function. So to do this, you need unified calling convention for LLM and code, so that it makes it invisible from the call side that if it is implemented this or that way. That's like very basic for programming, very basic idea. So, yeah, and then I have some practical additions also, like stateful tools and approval harness. Well, approval harness is it's the most annoying part of this, because there is no theory how it is to be done. I mean, there is a global part, like sometimes you want to run your agent in a sandbox environment and you don't care what it changes over there. So you just go with skip dangerous permissions, and it does everything. But then you run it in a different environment, and when you care about what it does, then it depends on local, on the tool that is used. So you have a tool that reads, and maybe you want, in this environment, you want to let the agent read everything it wants. But for writes, you want to ask for permission. So it depends on the tool. So only the tool writer knows what the tool does in general. So there are two policies. One is global and one is local, and then you need to just merge them to decide if this action is permission, if this action requires an approval or it doesn't. So yeah, approvals are very fuzzy, annoying, the worst part of writing this. Okay, so then I will show you some code in my system. I will show the declarative version of this. It's also possible to write it entirely in Python, but then actually this declarative form is more like better for presentation actually, because it shows more. It's So in this declarative form of the project is an analog of a program. So something that you use to do something. Yeah. And it has 4 elements. So it can have agents and tools. I mean, tools have Python functions, and agents are prompts. And actually, prompts are analog of function because they are called in the same way. And then you have the manifest which links all of this into one program. It's like a linker. Okay, so we start with data reports generator. It has two parts. It takes, yeah, okay. So the task for this program is to take directory with CSV data sets and produce some reports on it. Input, yes, input is a directory, and output is also a directory when it should write the reports. We shall build it twice. So the first version will be LLM-Only, and the second version will be with Python. And you will see that the calling convention doesn't change. So first is this manifest. It's like a config file. So one interesting. So we have some config elements here. For runtime, we can declare what is the maximum depth, because we don't want to use the Python maximum depth because it will be very big. So we need to limit this. It declares what is the entry point, where to start with this program, and it also lists all the agent and Python files, where to find the agents, where to find the Python tools, because the calling convention is by name, so it needs to first register all the names, and then it can call them, just like you do with a compiler. Yes. So an agent can use tool sets. You need to declare them, what it can use. There are some built-in tool sets that you don't need to code, so they are available at once. You don't need to link the file. So one of them is the file system tool which can list file, read files, write file. And then we have this analyze data set. That is another tool set. In the first version, it will be an LLM agent. In the second version, it becomes code. And that code still calls the LLM to do some part of its tasks. So here we have the orchestrator. It's an agent, and this is very, very similar to skills file. Just you have this front matter with YAML, some YAML declarations. It's very, very similar. And then you have the prompt for this agent. Then we have the analyzer. It's the same front matter syntax. Here is how it works. So it calls some tools, and so the first is a tool call to list the files. It wants to find what are the data files. it finds one, then it calls the analyze data set for this file. And then this analyze data set that is in this version is implemented as an agent. It just reads this file and returns this analysis, which is then written to a file. This is the approval. So you need to approve or deny this. Then we have, okay, so this version 1, when we do it many times, we can observe that, well, there are some parts that maybe would be better executed as Python instead of letting the LLM do everything. So stuff like reading or parsing CSV file, CSV data, computing statistics. This is all very deterministic and something that can be done better in code. But there are some other parts that we would rather leave to the LLM. So this is the version that does this. It does part of the work in code, in Python, and then it calls the LLM to write the narrative, to like take the raw data and write a narrative. And it is called in the same way. We don't need to change the part that calls this. So it makes the refactoring easier. So this is the stabilized run. It does the same thing. Then there is one less tool call because now we do this in code. So I call this way of refactoring from prompts into code stabilizing, because first you have code that is not deterministic, that executes each time in a different way, and then you stabilize it into a deterministic code. But you can also do the other way, like maybe you want to extend some function or to make it more flexible, and you want to change from code into a prompt. So it can also happen. So I call it softening. So stabilizing one way, softening the other way. And yeah, it gives, so when you evolve the system this way, then, well, it gives it a breathing space. You know. Every piece you stabilize becomes testable faster, cheaper, and auditable. So it's quite practical thing to do. The other way, it gets more flexible. So sometimes you will also do the other way. Progressive stabilization is like progressive confidence. Current status of this project, it's still like research grade, but it's not a vaporware. I have like more than 20 examples, working examples. You can try it. And the strongest part is this progressive stabilization and softening. I do it all the time, like refactor it or more forward and back. Then, and it is based on Pydantic AI, which is a very good base. So one line, okay, summary, and then we have resources. So there is this GitHub for my project. There is this short document theory about this probabilistic programming. Maybe someone will find it interesting. There are other docs like architecture. There is a README, all of this, and there are these examples. Also, the examples that I have shown here, they are also there, and I have ran them, so they should execute. Okay, questions?
program you've made with it?
Unfortunately, I haven't yet. I refactor it all the time, but I haven't yet get to write any practical thing with this.
So you said stabilizing and softening. Do you always decide as the user when this happens, or does an LLM decide?
Yes, for now it's the programmer that decides. Well, I think it might happen automatically that's like for the future. I have experimented also with bootstrapping, like you just give the LLM the instructions and it writes the sub-agent itself.
Mm-hmm.
But yeah, only on the side, only the prompt. I mean, I didn't write the code. But basically, it is well, you can still tell the LLM to write all the code and all the prompts just out of band.
One more, if there are no other people. I had a question. So, from your presentation, what I understand, one functionality equals one. Like, is the relation from stable and unstable stuff one-to-one or many-to-many? Like, can I have multiple prompts creating one functionality, or multiple functionalities like creating one prompt? Do you get what I'm saying?
Okay, so basically an agent is a prompt.
Yeah.
With some additional configs. So, and it has a name, and you call it by name. So there is one-to-one, like.
Okay, because for future, for example, I would like to refactor a functionality through another functionality. How would you work with it? The relation one-to-one makes it so that I can change it only through this way?
Well, you can also refactor the call site, but without changing the call site, then, you are stuck with the name. Because the call site calls a name. Well, I don't know. Maybe that is for the future. But, it's just like in normal programming. You have functions and you call them by name. I don't think that, like having a set of functions and I don't know how would it be supposed to work. But of course you can refactor one agent into several agents by, calling from this agent other agents, just like you do with a function. Okay, so I don't see any more questions. Thank you.